Section 6 of The Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rick Vina. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 3, Geology and the Church, Part 2. Next among the notable workers was the versatile B.F. Guettard, who traveled through France, England, Germany, and Poland, and whose great desire it was to reproduce his scientific observations on maps. Guettard's mineralogical map of France and England gives so much accurate information regarding the local occurrence of rocks and minerals, and the position of mines, quarries, fossil localities, mineral springs, hot springs, and coal, that it can still be used with advantage. The map is not colored. Guettard described the processes of land denudation effected by the solvent and destructive agency of rain and rivers, and by the abrasion of the waves. This is probably the first paper in which a systematic account of denudation is given in its relation to changes in the configuration of the earth's surface. The most brilliant of Guettard's achievements was his discovery of the volcanic rocks in the Auvergne region. Nicolas Desmarest, a French professor, opposed Guettard's erroneous conception that the Auvergne basalt pillars had crystallized from a watery fluid, and demonstrated the resemblance of the Auvergne basalt to certain recent lavas. He was supported by F. de Saint-Fond, 1742 to 1819, professor in the Museum of Natural History in Paris, who brought forward conclusive evidences of the igneous origin of basalt. Toward the close of the 18th century, the idea of distinguishing the mineral masses on our globe into separate groups and studying their relations began to be generally diffused. Of these investigators, Pallas and Saussure were among the most celebrated whose labors contributed to this end. After an attentive examination of the two great mountain chains of Siberia, Pallas announced the result that the granitic rocks were in the middle, the schistose at their sides, and the limestones again on the outside of these, and this he conceived would prove a general law in the formation of all chains composed chiefly of primary rocks. In his Travels in Russia in 1793 and 1794, he made many geological observations on the recent strata near the Volga and the Caspian, and adduced proofs of the greater extent of the latter sea at no distant era in the earth's history. His memoir on the fossil bones of Siberia attracted attention to some of the most remarkable phenomena of geology. He stated that he had found a rhinoceros entire in the frozen soil, with its skin and flesh. An elephant found afterward in a mass of ice on the shore of the North Sea removed all doubt as to the accuracy of such a remarkable discovery. The subjects relating to natural history which engaged the attention of Pallas were too multifarious to admit of his devoting a large share of his labors exclusively to geology. Saussure, on the other hand, employed the chief portion of his time in studying the structure of the Alps and Jura, and he provided valuable data for those who followed him. Quirini, in 1676, contended that the diluvian waters could not have conveyed heavy bodies to the summit of mountains, since the agitation of the sea never extended to great depths, and still less could the testacea, as some pretended, have lived in these diluvian waters, for "the duration of the flood was brief, and the heavy rains must have destroyed the saltness of the sea." He was the first writer who ventured to maintain that the universality of the Noachian cataclysm ought not to be insisted upon. The great mathematician Leibniz published his Protogaia in 1680. He imagined this planet to have been originally a burning, luminous mass, which, ever since its creation, has been undergoing refrigeration. When the outer crust had cooled down sufficiently to allow the vapors to be condensed, they fell and formed a universal ocean, covering the loftiest mountains and investing the whole globe. The crust, as it consolidated from a state of fusion, assumed a vesicular and cavernous structure, and, being rent in some places, allowed the water to rush into the subterranean hollows, whereby the level of the primeval ocean was lowered. The breaking in of these vast caverns is supposed to have given rise to the dislocated and deranged position of the strata, which Steno had described, and the same disruptions communicated violent movements to the incumbent waters, whence great inundations ensued. The waters, after they had been thus agitated, deposited their sedimentary matter during intervals of quiescence, and hence the various stony and earthy strata. We may recognize, therefore, says Leibniz, a double origin of primitive masses, the one by refrigeration from igneous fusion, the other by concretion from aqueous solution. By the repetition of similar causes, the disruption of the crust and consequent floods, alternations of new strata were produced, until at length these causes were reduced to a condition of quiescent equilibrium, and a more permanent state of things was established. Robert Hooke (1635 1703) was one of the most brilliant, ingenious, and versatile intellects of the 17th century. Among the many subjects to which he directed his attention and on which his remarkable powers of acute observation and sagacious reflection enabled him to cast light, some of the more important problems of geology must be numbered. In 1705 appeared the Posthumous Works of Robert Hooke, M.D., which contained a discourse on earthquakes. However trivial a thing, he says, a rotten shell may appear to some, yet these monuments of nature are more certain tokens of antiquity than coins or medals, since the best of those may be counterfeited or made by art and design, as may also books, manuscripts, and inscriptions, as all the learned are now sufficiently satisfied has often been actually practiced. And though it must be granted that it is very difficult to read them, the records of nature, and to raise a chronology out of them, and to state the intervals of the time wherein such catastrophes and mutations have happened, yet it is not impossible. He accounts for the shells found in mountains by saying that such things may be due to the action of earthquakes, "which have turned plains into mountains, and mountains into plains, seas into land, and land into seas, made rivers where there were none before, and swallowed up others that formerly were, and which, since the creation of the world, have brought many great changes on the superficial parts of the earth, and have been the instruments of placing shells, bones, plants, fishes, and the like in those places where, with much astonishment, we find them." About 1690 appeared Thomas Burnet's Theory of the Earth. The title is characteristic of the age, the sacred theory of the earth, containing an account of the original of the earth and of all the general changes which it had already undergone or is to undergo till the consummation of all things. Even Milton had scarcely ventured in his poem to indulge his imagination so freely in painting scenes of the creation and deluge, paradise and chaos. He explained why the primeval earth enjoyed a perpetual spring before the flood, showed how the crust of the globe was fissured by the sun's rays, so that it burst, and thus the diluvial waters were let loose from a supposed central abyss. Not satisfied with these themes, he derived from the books of the inspired writers, and even from heathen authorities, prophetic views of the future revolutions of the globe, gave a most terrific description of the general conflagration, and proved that a new heaven and a new earth will rise out of a second chaos, after which will follow the blessed millennium. The celebrated naturalist John Ray (1627 1705) participated in the same desire to explain geological phenomena by reference to causes less hypothetical than those usually resorted to. In his essay on Chaos and Creation, he proposed a system agreeing in its outline and in many of its details with that of Hooke, but his knowledge of natural history enabled him to elucidate the subject with various original observations. Earthquakes, he suggested, might have been the second causes employed at the creation in separating the land from the waters, and in gathering the waters together into one place. He mentions, like Hooke, the earthquake of 1646, which had violently shaken the Andes for some hundreds of leagues, and made many alterations therein. In assigning a cause for the general deluge, he preferred a change in the earth's center of gravity to the introduction of earthquakes. Some unknown cause, he said, might have forced the subterranean waters outward, as was perhaps indicated by "the breaking up of the fountains of the great deep." Among the contemporaries of Hooke and Ray, John Woodward (1665 1722), a professor of medicine, had acquired the most extensive information respecting the geological structure of the crust of the earth. He had examined many parts of the British strata with minute attention, and his systematic collection of specimens, bequeathed to the University of Cambridge and still preserved there as arranged by him, shows how far he had advanced in ascertaining the order of superposition. He conceived "the whole terrestrial globe to have been taken to pieces and dissolved at the flood, and the strata to have settled down from this promiscuous mass as any earthy sediments from a fluid." In corroboration of these views, he insisted upon the fact that "marine bodies are lodged in the strata according to the order of their gravity, the heavier shells in stone, the lighter in chalk, and so of the rest." Ray immediately exposed the unfounded nature of this assertion, remarking truly that fossil bodies are often mingled heavy with light in the same stratum, and he even went so far as to say that Woodward "must have invented the phenomena for the sake of confirming his bold and strange hypothesis," a strong expression from the pen of a contemporary. It is interesting to turn from the physico-theological disputes of the Germans and English to follow the steps of the Italians and witness the real progress they were making at this time, the while that they refuted and ridiculed the theories of Burnet, Woodward, and Ray. An illustrious observer in the geological domain appeared in Italy when Steno, in his 25th year, was rapidly rising into fame as an anatomist. Antonio Vallisneri (1661 1730) became professor of medicine in Padua. In the course of his journeys he had opportunities of seeing much of the geology of his native country, and of forming a clearer conception of the fossiliferous formations of the great central mountain chain than any one had done before him. His works were rich in original observations. He attempted the first general sketch of the marine deposits of Italy, their geographical extents, and most characteristic organic remains. In his treatise on the origin of springs, he explained their dependence on the order and often on the dislocations of the strata, and reasoned philosophically against the opinions of those who regarded the disordered state of the earth's crust as exhibiting signs of the wrath of God for the sins of man. Although reluctant to generalize on the rich materials accumulated in his travels, Vallisneri had been so much struck with the remarkable continuity of the more recent marine strata from one end of Italy to the other, that he came to the conclusion that the ocean formerly extended over the whole earth, and after abiding there for a long time, had gradually subsided. The last and not the least of the cosmogonists was G. L. Leclerc de Buffon (1707 1788), one of the greatest pioneers, who figured so conspicuously in the history of France. At first interested in physics and mathematics, he gradually broadened his field of observation, taking in the whole realm of nature. He adopted the theory of an original volcanic nucleus, together with the universal ocean of Leibnitz. By this aqueous envelope the highest mountains were once covered. Marine currents then acted violently, and formed horizontal strata by washing away solid matter in some parts and depositing it in others. They also excavated deep submarine valleys. The level of the ocean was then depressed by the entrance of a part of its waters into subterranean caverns, and thus some land was left dry. Soon after the publication of his Natural History, in which was included his Theory of the Earth, he received an official letter, dated January 1751, from the Sorbonne, or Faculty of Theology in Paris, informing him that 14 propositions in his works "were reprehensible and contrary to the creed of the Church." The first of these obnoxious passages, and the only one relating to geology, was as follows: "The waters of the sea have produced the mountains and valleys of the land. The waters of the heavens, reducing all to a level, will at last deliver the whole land over to the sea, and the sea, successively prevailing over the land, will leave dry new continents, like those which we inhabit." Buffon was invited by the college in courteous terms to send in an explanation, or rather a recantation of his unorthodox opinions. To this he submitted, and a general assembly of the faculty having approved of his declaration, he was required to publish it in his next work. The grand principle which Buffon was called upon to renounce was simply this: "that the present mountains and valleys of the earth were due to secondary causes, and that the same causes will in time destroy all the continents, hills, and valleys, and reproduce others like them." Now, whatever may be the defects of many of his views, it is no longer controverted that the present continents are of secondary origin. The doctrine is as firmly established as the earth's rotation on its axis, and that the land now elevated above the level of the sea will not endure forever is an opinion which gains ground daily in proportion as experience of the changes now in progress is enlarged. Taglioni (1751) opposed Buffon in his theory regarding the origin of valleys. Buffon attributed them principally to submarine currents, while the Tuscan naturalist labored to show that both the larger and smaller valleys of the Apennines were excavated by rivers and floods, caused by the bursting of the barriers of lakes after the retreat of the ocean. He was a contemporary of Werner, who ushers in a new era. End of section 6.